Hi, so our first speaker for this is Sergei Gukov from Caltech, who will be speaking about the role of AI in mathematical research with a parentheses around the RE. All right, take it away.
So these are some of the papers on which this talk is based. It's going to be a relatively short talk. So if you want to read more, I want to advertise this comprehensive summary that we did for NSF about a year ago. Well, the project started about a year ago and then was completed a few months ago in the fall 2025 about the future of AI in mathematical and physical sciences. And there is also a technical paper. I'll mention several works on which this perspective, it's very personal perspective actually, is based. But if you want to read more about search and hard search and RL for a particular problem, which in this case is combinatorial group theory. So the second paper on the screen is where I'm drawing some of my lessons. Okay. So I want to start with something fun that some of you probably have heard about. So 100 years ago, there was this horse, very famous in fact. Clever Hans is the name of the horse. And the horse would go around, give tours, and it would seem that the horse is able to do many non-trivial tasks that a human can do, in particular mathematical reasoning. So this master of the show, the guide, would ask was is fünf und fünf, and the horse would tap 10 times, which is the correct answer. 5 plus 5 is 10. And that was actually very impressive. So that was going on for several years, and horse was extremely popular. In fact, since it's remembered up to present day, I think the horse is probably more famous than me going giving talks because I don't expect to be remembered 100 years from now. But then it took about 3 or 4 years to figure out what's going on. In fact, I'm actually surprised that it took that long. Someone did a study and noticed that if the horse cannot see this master of the show, the person or the guide, it actually cannot give the correct answer. And what turned out is that the horse is actually picking up on very subtle cues that the person, the guide, is giving. For example, a subtle nod after the horse is stepping 10 times. So it's actually not that horse was able to do mathematical reasoning. Horse definitely had talents, but not the ones identified or presented. And part of the reason the horse is actually famous up to present day is that in AI research, there is this effect called Clever Hans effect. And it doesn't necessarily have super positive connotation. From AI perspective, it roughly means that there is leakage or some of the test data is present in the training data, which is not that great. Anyway, so I was thinking what would be the modern day analog of Clever Hans today, 100 years later. And as I was working on various projects this summer, I'm involved in some chat group with many colleagues who are interested in AI and math. And one of them shared this very simple, interesting question. So later in the talk, I'll be telling you about very ambitious advanced projects, but this is a very simple one. So this was this summer, and the legacy model 4.0 of ChatGPT would do this. So if you ask it, what is 9.9 minus 9.1? I mean, it sounds like a very simple arithmetic question, and yeah, not much of a super intelligence or advanced research that we'll be talking about later. And strangely enough, you repeat a number of times. It's of course stochastic and statistical. There is probability involved, but roughly 70% of the time, I would get this answer. And the trick here, of course, is that I add a zero. It's not just 9.9 minus 9.1, it's 9.10. An extra decimal that, of course, doesn't change the math, but the model would surprisingly give the answer minus 0.2. Okay. So this is a very fun effect. Actually, I don't know if they fixed it at this point. So you may try to go and call 4.0. Now, of course, there higher level models, but you can probably still access it, and maybe it still gives -0.02 on some occasions. And from AI point of view, it's actually good to think why this happens. So there are at least two reasons for this answer. But in my mind, so I spent maybe a couple hours playing with it, and that was my best candidate for clever hacks. And I personally like all the modern tools and models, but this talk will be in some sense about their limitations. And understanding limitations may help us develop these tools better and therefore better assist not only mathematical research, but also education and humanity in general. So there are many different levels of math problems, and especially when I give general audience talks, it's important to clarify what we really mean by AI doing mathematics, because there are many gradations. For example, in school, there is elementary school type problems, middle school problems, high school problems, then some math competitions. Then we go to college. There are undergraduate, graduate level problems. Then there are problems that we give to our PhD students, and if they complete it, they get a PhD in mathematics. Then there are high level problems that we kind of struggle with and wouldn't give to graduate student. And then there are outstanding problems that we actually don't know how to solve. Some would be of a caliber of a Mincioni, some would be of the caliber of Millennium Prize. And it's important to distinguish these gradations. So current modern AI tools, they're improving. They're getting better every year or two, and they move through this hierarchy slowly down. And the current general purpose tools, like LLM-based tools, they definitely reach the level of math competitions, maybe not perfectly. So I'll tell you a little bit more about it this summer, and you heard about it in the previous talk. None of the models managed to solve all 6 problems with flying colors, but models solve 5 problems, which is not bad enough to get gold on IMO, for example. But the reason I go through this list is to emphasize what this talk is and is not about. So I'm not going to be focusing on most of this hierarchy. I'll ask the following question in this talk. What would it take for AI to get all the way to the bottom? So basically help us beyond capabilities that we as humans can provide to tackle mathematical problems and help us with really ambitious big problems. And I'll tell you a little bit about my personal journey. And I've been working in this domain for 7 or so years. And I have to say, I'm not fully convinced that this will happen. So that's why I want to ask a question: what would it take so we can focus and put more resources there to actually develop the right tools? So there are several reasons to be cautious and concerned, or skeptical, if you wish. So, for example, one of the companies, Epoch AI, and at some point I helped them to build benchmarks. So it produced several good benchmarks, Frontier Math. And this company did some research, and this is a plot that illustrates that if you just try to develop tools by scaling LLMs, there are several reasons to be worried or cautious, because first of all, we're running out of clean data, and that's what LLMs are mostly trained on, and this is what the main graph illustrates. In fact, they even predict when this sort of gonna happen. But I also want to add to this that scaling is hard because most scaling curves in AI research are logarithmic, and logarithm is a very slow function. So if you want to improve performance by 100x, you would, through LLM, you would have to put 10 to the 100 or 2 to the 100 more compute or size of the model or training data. And this is not quite feasible. And then pay attention to the big numbers you'll see later in the talk. So from my personal, everything I say again is based on just personal perspective. So my journey started about 7 years ago, and by now I have a number of research level papers published in NeurIPS, ICML, ICLR, on applying AI to knot theory, combinatorial group theory, commutative algebra, low-dimensional topology, and I'm certainly open to exploring other areas. In various advisory roles, I was also involved, and as outside roles, I was involved in helping other organizations. I already mentioned Epoch AI, which was really good for developing benchmarks, especially for research level math. I learned a lot from advisory group to AMS, and I helped Harmonic to build Aristotle, and more recently was helping Google DeepMind with Alethea, which did quite well on some of the Erdős problems, or at least that was the context where you might have heard these developments. In the talk, I'll try to focus less on mathematics, which may be a little bit surprising, but I want to really focus on sort of computer science aspect of it. So all my life, I love building bridges and connecting different fields. So now I'm very excited about connecting pure mathematics to computer science. And one of the key points of this talk is that by trying to develop AI tools, which potentially can help us with research level math, we can actually contribute a lot to AI development itself. So I'm approaching this from the viewpoint of sort of software engineering, if you wish. And again, the question I'm asking here is that through this series of works in the past 7 years, I learned a number of lessons, and one of them is that, yes, AI is definitely a very useful tool. So it can assist me in a way that accelerates my professional research by 10x, potentially 100x, but then question, how far can it go? And that's the question I want to ask. Again, approaching it from most ambitious class of problems that we want to solve in mathematics. So if it hasn't been discussed before already, I want to make sure that we cover some of the basics. So AI consists of different areas, one of which is machine learning. And machine learning in turn consists of 3 basic subfields. Supervised learning, which is where regression tasks belong. It's roughly speaking, finding the best fit or finding a function from X to Y. Unsupervised learning is a little bit more interesting from computer science perspective. And mathematically, this is where these are types of models that are good at recognizing patterns when we have unstructured or unlabeled data. So those of you who've heard of murmurations, for example, that's where unsupervised learning played an important role. This talk will focus actually mostly on reinforcement learning, which is the third and arguably the most delicate or interesting aspect of machine learning. That's the one which teaches AI models to play games, to interact with environment, learn lessons, and make better decisions. So autonomous vehicles, self-driving cars, this kind of things, or board games, all of that is fueled or powered by reinforcement learning. And reinforcement learning is a very exciting, at least to me, branch of computer science and AI research, because again, you can literally think of it as playing games. So that's why it's a lot of fun. And the history of modern reinforcement learning goes back maybe 10, 12 years. So here I mentioned one of the very first algorithms. So when you study RL models, you have to choose which algorithm you want to use. And there are maybe a dozen or a couple of dozen very standard ones, which we teach in CS courses. And one of the first called DQN or DeepQ network was proposed in this paper from DeepMind. That's actually one of the first DeepMind big results before AlphaGo and other things. And as you can see, this is real figure 1 from the paper. So the paper talks about this algorithm that now all AI researchers know, and it's again used mostly for teaching. It's cool, but it's not like super advanced. And at that time, we didn't talk about board games, the benchmarks were mostly Atari games, and the story of GQN is very interesting. It's actually described in this recent movie from DeepMind, but and it wasn't a straight journey, so there were lots of interesting challenges and so on. But eventually, this algorithm DQN managed to figure out how to play games well just from pixelated screens. And in this talk, I'll bounce back and forth between sort of pure AI or computer science perspective and applications to mathematics. So now let's go to mathematics. Here, there are several tasks we usually do as mathematicians. Sometimes we want to prove statements that we already know or believe to be true. So we want to have rigorous proof. And for this, of course, Lean and other formal languages are super useful. So they basically operate as computer code, and if it compiles, then we can believe that the proof is more or less correct. There is a caveat there, but I'll skip it for now. And if you ask this question that I was asking in the very beginning, what is the difference between like easy problems or easy theorems and hard? At the very basic level, one metric could be the length of the Lean steps. So if we break down everything to basic Lean steps, some of the theorems have reasonably short proofs, such as the ones shown on the screen. But if you ask for a very advanced theorem, then proof is probably going to be 1,000 or maybe even millions lines of Lean code. And maybe that's the reason we didn't come up with a proof of Riemann hypothesis yet. So whatever it is, it's most likely to be very long in terms of basic Lean steps. So another thing that we do in mathematics, so yeah, in terms of proofs, it's the length of the proof, the horizon. So another thing that we do is we search for examples or counterexamples. And this is a problem from combinatorics, namely the search for Ramsey numbers. The problem has to do with, in this particular case, of two-color colorings of complete graphs on, let's say, n vertices, and you're asking under what conditions you can always find or not find a complete either red or blue subgraph on either R or S vertices. And these are typical extremal problems in combinatorics. Details, if you haven't seen it before, are not so important. What's important is that for these particular problems, finding the right example or counterexample can be very much like a search of a needle in a haystack. For example, in order to produce this number 18, you have to show that certain conditions are not satisfied for 17. And a counterexample that you would find for a 17 vertex graph would be 1 out of 10 to the 26. So it's a search, and many math problems are kind of like a search. It's either for example, counterexample, or search for sequence of Lean steps. And what distinguishes, at least very roughly, hard problems from easy ones is the depth of this search. How hard is it to find the instance we're looking for? So from computer science, whether we're looking for a proof or for example or counterexample becomes kind of secondary, and it's the sparsity of it that becomes the bottleneck or the main challenge. So to summarize, math is fun, and one reason it's fun is that it could be viewed as a game, very much like games, board games like chess and Go. And hard math is when the game gets very long and the search gets very deep and hard. And then it's an interesting discussion. What makes math problems hard for AI? Is it the same way as we human perceive it? So this third point I'll leave for maybe panel discussion, or I'm sure it will be discussed throughout the day. And I'll focus mainly on this hardness and long games. So this is something that's actually a challenge in computer science and AI research, because current AI systems, so I very often these days go to CS conferences like NeurIPS and ICML, ICLR, and people recognize this challenge, but it's very hard to overcome it. So there is no easy, simple solution. So this is cutting edge of AI research because that's where AI needs new ideas, new discoveries, maybe similar to Transformer Revolution. Because in problems that, like Atari games, for instance, or even board games like chess and Go, one thing that AI systems quickly learn is what not to do. This is what our parents teach us, so we learn to fail quickly. But imagine that you're playing a very long horizon game, either very complicated infinite size maze or game of chess, which would be on a board of million times million. So then you could go for thousands of steps and never know if you're on the right path or wrong path. So this is kind of challenges that we see in mathematics from computer science perspective. Also, another important aspect of it is, or another way to look at it is out of distribution generalization. In this challenging math problems, we need to teach AI models, or be it reinforcement learning for specificity, to make steps very far outside of training data, not just a couple of inches away, megaparsecs away. Another aspect or way to look at this is that many models can learn very quickly what to do on a generic case, but it's important to ask what is the distribution of hardness or interesting cases, and is extreme case very different from generic case? And if the answer is yes, then again, this is where current models hesitate. So what happens in some of these difficult math problems, for example, I mentioned in the beginning Andrews-Curtis conjecture, and I'm not going to talk about mathematics of it, but I'll talk about the challenge it presents to computer science. The challenge is that the problem initially looks very much like typical reinforcement learning problem. You start with some initial state. You need to train a pathfinder to find a sequence of operations or actions to get to a goal state, a finish line. And it has very well-defined reward for what it means to make progress. But the problem is that on generic cases, the situation is relatively easy in the sense that the path could be, say, polynomial in the length of the input. But then, at least in the Sanders-Curtis conjecture and also in many other problems, what happens is that next to generic instances of this type, in the board on which we're playing the game, there are sprinkled very rare initial states such that you can reach the goal state from them, but your path would be super exponentially long in the size of the input. So it would be like 2 to the 2 to the 2 some number of times. And it's very hard. So this is definitely in the tail of distribution, and it's extremely hard for AI system to learn those outlier events. They're very important to us mathematically, but it's very hard to train on generic data to make such inferences. And the point I'm trying to make is, if you look at board games, yes, I know that chess may look complicated, but from this perspective, it's actually an extremely easy game. Because, first of all, typical game of chess and Go lasts only 30, 40 moves. And if you ask for longest games of chess, for example, longest recorded game lasted 269 moves. So you see, it's only 1 order of magnitude difference, and it's not much. It says that generic games and extreme games are pretty much similar to each other. And again, it's not very long. If you think about number of moves as being roughly equivalent to number of lean steps, this is not very long horizon game. And the same goes for the game of Go. Again, there the difference between extreme hard games and generic games is also just 1 order of magnitude, and it's only slightly harder here. So I mentioned that this is a challenge from AI perspective. And again, I'm approaching this talk almost like a software engineer trying to solve the problem, or AI researcher. And the problem is known in the community. It is recognized, but it's not something that's easy to solve. So in this paper that I showed you earlier, where a DQN algorithm was introduced by DeepMind, we usually focus on success stories. And this plot on the left shows performance of DQN, that algorithm, on various Atari games. And the line, which may be hard to see in the middle, that's the average human performance, or yeah, maybe human expert, I can see. But the point is that most of the games are above this line. So this DQN algorithm did really well. But then if you look at the lower part of the diagram, you see that there is one game that got exactly 0 score. So it means that this algorithm never even accidentally succeeded in winning this game. And the name of the game is Montezuma's Revenge. So in reinforcement learning community, this game became kind of like a challenge. So naturally, people try to build RL models, that reinforcement learning models that try to solve this game. There is nothing terribly special about it as far as you can see. It's a game where you have to navigate labyrinth, collect certain artifacts, not much different from many others maybe. But in RL community, this became an obsession. So starting from that time, 2012, 2013, many different groups try to develop new tools, new algorithms. And here on this plot, you should basically see some of these developments indicated by, so each point is a group or attempt, and you see various variations of DQN algorithms, then various others, such as PPO. These are also pretty standard RL algorithms. And it took a while for the community, RL community, to search in a space of algorithms to find something that finally works. So challenge here is that if you try to work on harder problems, not only your problem may be like a needle in a haystack, your search for the right algorithm to do well is also like a needle in a haystack. You have to go through 50 or 100 algorithms before you find something that works well. And this is what approaching these hard problems really feels like in from AI research perspective. Speaking of needles in the haystack, on LLMs there was this pressure testing benchmark called needle in the haystack. Here it shows that at least at the time of the performance or testing, again, LLMs, they're not devised to look for outliers, so naturally they didn't do well on needle and haystack kind of searches. And this is probably familiar to you, and I want to circle back to this study that Epoch AI was doing. That again, LLMs are really good at tasks that involve many generic elements, but the more specialized we get, the more it starts hallucinating or hesitating. So with this in mind, or after this experience, a couple of years ago, we decided to build a new lab at Caltech, which now is kind of fully focused on this rarer searches, rarer events, or needle and haystack type searches. And maybe one useful information, especially for younger members of the audience, is that we're hiring. So the lab opened up last year. So if you're interested, please apply. So the logo of this lab is Math plus AI equals AGI, because again, these outlier events are really relevant. Performance on these events is really relevant to developing systems that can do out of distribution generalization, and that's prerequisite for AGI. And from the development point of view, it's a very standard computer science or AI research loop where you try some new system, you evaluate how it performs, then you analyze what happened, why it doesn't do so well, you go back to the drawing board, and you try to develop a new, better model, and then again, you repeat this some number of times, usually pretty large number, could be 50, could be even 100. And the only difference for our lab is that we're essentially using mathematical hard math problems as environments to do this research. So I want to conclude this talk by summarizing that, at least in my mind, for reaching that level that I mentioned in the very beginning of the talk of not only research level math, and yes, it surely is amazing assistant to us, but going beyond that to sort of ASI level, we need really good out of distribution capabilities. We need to look for needles and haystacks, or black swans, or unicorns, as they're sometimes called. And such challenges or need for such systems that can identify black swans, identify needles in haystack, or out of distribution generalization. Of course, this is not just special to mathematics. So there are many other domains where rare events with very disproportionate reward play an important role. For example, extreme weather phenomena or financial markets. And I want to conclude by paraphrasing a quote by famous mathematician Vladimir Arnold, who said that mathematics is the part of physics where experiments are cheap. So in my talk, I wanted to convey that by trying to develop AI tools that do well in math, we can actually contribute a lot to AI development. So in other words, mathematics is the part of AI research where experiments are cheap. And with that, I want to thank you for your attention, and I'll be happy to answer questions.